Have you ever actually stopped to think about what happens behind the scenes when you log into your bank account, or order some takeout, or send a private document over the web? We do it dozens of times a day, completely taking it for granted. But fundamentally, the internet is like an incredibly noisy, chaotic city full of people who just love to listen in on other people's business. Every single time your phone or your computer sends something out into the world, it's a bit like whispering a highly sensitive personal secret in the middle of a packed Starbucks. If you aren't careful about how you do it, literally anyone sitting nearby can hear exactly what you're saying. Well, welcome to this explainer. Today, we are going to unpack the exact, fascinating technology that allows us to have totally private conversations in that incredibly crowded, very public room.
Okay, so let's really dive into this scenario. When you're surfing the web from a public network, let's say you're chilling in an airport lounge or a hotel lobby or that local coffee shop we just mentioned, you frankly have absolutely no idea who is sharing that exact same connection with you. And without the right protection, a hacker sitting just a few tables away, sipping a latte, can easily grab your messages right out of the air. They could intercept your credit card details. They could silently change your online food order from a tiramisu to a cheesecake just to mess with you. Or worst of all, they could even pretend to be your bank. It's a completely open environment. Your data is just floating through the airwaves, completely vulnerable to anyone with even a basic understanding of how network traffic works.
And honestly, that terrifying reality is exactly why we rely on the absolute hero of our explainer today, Transport Layer Security, or TLS. Now, you might not know the name, but you definitely know what it does. TLS is the technology working tirelessly behind that reassuring little padlock icon you see up in your browser's address bar. It acts as the quiet, invisible guardian for all of our connections. Think of it like this. TLS gives you an encrypted, locked briefcase so no one can read your message. It gives you a signature wax seal so the person receiving it knows for a fact it hasn't been tampered with, and it provides a strict digital ID check to confirm you aren't accidentally handing your data over to a villain in disguise. Simply put, without TLS, the web would be a total free-for-all of stolen passwords and widespread identity theft.
So, to really understand how this magic works, here is our roadmap for today's explainer. 1. The hostile internet. 2. The three big threats. 3. From SSL to TLS. 4. Mutual TLS, or MTLS. And finally 5. TLS in practice.
All right, let's jump right into part 1, the hostile internet.
We need to start with a foundational truth, and this is something that every single software developer and network engineer needs to internalize right from day one. The internet was absolutely not built with trust in mind. Zero. It was designed purely for routing. The entire goal was just to send messages from point A to point B as fast and efficiently as possible. When you send a message, it doesn't just travel through some magic, secure pipe straight to its destination. Not at all. It might cross through your local service provider, jump across an ocean on a massive undersea cable, and bounce through a totally random router sitting in Iceland. Your data passes through dozens of machines, routers, and switches that you do not control, and honestly, you don't even know exist. You don't get to choose who carries your messages. Because of this, you just have to assume the network itself is hostile. Malicious internet service providers, compromised public Wi-Fi networks, uninvited middlemen, they're just par for the course. TLS doesn't try to magically fix this wild, untamed network. Instead, it assumes the network is already compromised and it focuses entirely on securing the data itself. Which brings us nicely to part 2, the three big threats. Okay, once we accept the grim reality that the network is fundamentally hostile, we need to categorize exactly what kinds of attacks we're looking at. All the chaos of network security really distills down to 3 distinct major problems: eavesdropping, tampering, and impersonation. These are the specific dangers your data is facing every second it's on those open networks. And the brilliant thing about TLS is that it's specifically engineered to act as a simultaneous shield against all 3 of these attack vectors. Let's break them down one by one so we understand exactly what we are defending against here. First up on the list, eavesdropping. This is exactly what it sounds like: the unauthorized interception and reading of unencrypted messages. Imagine your data as a postcard. Without TLS, anyone sitting anywhere between you and the server can simply flip that postcard over and read your data as it floats by. If you're sitting on an unsecured public Wi-Fi network, an attacker using entirely free, easily available software tools can just sniff the traffic. They can literally see what websites you're visiting, the forms you're filling out, the files you're downloading, all of it in plain text. It's a privacy nightmare.
TLS solves this by encrypting the connection from start to finish. Even if someone manages to grab your data packets out of the air, all they're going to see is absolute mathematical gibberish. It's like sealing your message inside a locked, impenetrable envelope before it ever even leaves your device.
Now, the second big threat is tampering. Let's say an attacker knows they can't actually read your encrypted message, but what if they just scramble it? Or worse, silently change it? Imagine you're filling out a payment form online. You type in the correct bank account number. Everything looks good. But a hidden attacker quietly intercepts it and swaps your account number with their own before it reaches the server. You click send, thinking everything is fine, and your money goes straight into a criminal's pocket. Tampering is terrifying mainly because it is usually completely invisible to the user until the damage is already done. TLS protects against this using message integrity checks. Think of these like cryptographic checksums or message authentication codes. It acts just like a tamper-evident seal on a medicine bottle. If even a single byte of your data is altered in transit, the seal breaks, the math no longer adds up, and your browser immediately discards the message, completely shutting down the attack.
And the third major threat is impersonation. What if the server you're talking to isn't actually your bank, but a really, really clever fake? I mean, it might have the exact same logo, the exact same login page, the same color scheme. You could confidently type your password in and send it straight to a hacker. This is called spoofing, and unfortunately, it happens all the time. TLS solves this massive problem by requiring digital certificates. When your browser connects to a secure site, the server must present its certificate. Think of this as a highly secure digital ID card that's been officially signed by a trusted third-party certificate authority. Your browser checks this ID card to mathematically prove the server is exactly who it claims to be, well before it ever lets you send a single byte of your private data.
To really see why this matters in practice, let's look at a classic man-in-the-middle attack. Back in high school, the authors of the source material we're looking at today used a network sniffer tool called Cain and Abel on their school's computer network. By basically impersonating the local router, they could silently intercept and read all of their classmates' Yahoo Messenger chats in plain text. Why was this so easy? Because those early chat applications simply didn't use encryption. Anyone on the network could be a silent eavesdropper and nobody would know. But fast forward to today, with TLS enabled, that story changes entirely. Even if that same interception happens on the network, the data goes out completely encrypted. The attacker can't read a word of it. And if they try to alter the message just to cause chaos, the recipient's computer immediately detects the tampering because that digital signature won't match. The attack is completely and totally neutralized.
So, how did we get this incredible protection? Let's move to part 3, from SSL to TLS.
Now, you've probably heard the terms SSL and TLS thrown around interchangeably in tech blogs or meetings, but they are absolutely not the same thing. SSL, which stands for Secure Sockets Layer, is basically the ancestor of TLS. It was a pioneer, it had the right idea, but its armor had some incredibly serious holes. Over time, hackers figured out clever ways to trick browsers into using weaker encryption. This is a vulnerability known as a downgrade attack. They could also, in some cases, steal the actual session keys by exploiting deep bugs in the code. Because of these fatal flaws, all versions of SSL have been officially retired for years. They are considered entirely unsafe. TLS picked up right where SSL left off, redesigning and heavily strengthening every single part of the connection. Today, and specifically since 2018, TLS 1.3 is the secure, gold standard preferred modern protocol.
To really understand why we absolutely had to upgrade, we need to take a quick look at the old SSL handshake. In this process, let's say we have Alice, who is the browser, and Bob, who is the server. They say hi, they agree on their encryption methods, and they exchange certificates. But here is the critical, fatal vulnerability when they go to actually establish their secure connection. Alice encrypts a shared secret key and physically sends it over the network to Bob. Now yes, it is encrypted, but sending the actual literal secret key across a hostile internet inherently introduces a massive risk. If a patient attacker records that encrypted conversation and then eventually breaks that specific encryption, maybe years later when computers are much faster, they now have the key to the entire conversation. They can go back and decrypt absolutely everything that was sent. Now contrast that massive flaw with the modern TLS handshake. There is a fundamental, game-changing difference in how they establish that shared secret today. Instead of Alice sending a secret over the wire to Bob, they use something called elliptic curve cryptography, or ECC. And this is just a brilliant piece of mathematics. It allows Alice and Bob to exchange strictly public, non-secret information over the open network. And then, using that public info, each of them independently calculates the exact same shared secret on their own local machines.
The actual shared secret never ever travels across the network, not even encrypted. It is mathematically impossible for an eavesdropper to figure out the shared secret just by watching the public exchange. It's truly incredible. So let's just summarize these modern TLS steps, because they really are the very foundation of trust on the internet today. Step 1. Alice and Bob agree on how they will communicate, establishing the rules and encryption methods. Step 2. They exchange those digital certificates to definitively prove their identities. Step 3. They use that brilliant elliptic curve cryptography to mathematically generate a shared secret entirely independently, acting as a one-way trapdoor function. And finally, Step 4. They use that brand new shared secret to encrypt all future communication for that session. It's a literal conversation that establishes a mathematically locked briefcase and a tampered-proof wax seal, all without ever exposing the key to the public.
All right, moving on to part 4, mutual TLS, or MTLS.
Standard TLS secures our public web browsing perfectly. It's great when you're visiting a blog or a store. But what happens when we're dealing with highly sensitive internal backend systems? What if we have critical microservices talking to other microservices deep inside a corporate network? Well, in standard TLS, only the server has to prove who it is. Your browser remains completely anonymous until you actively decide to type in a password. But in mutual TLS, trust is a two-way street. Before any data is exchanged whatsoever, Alice, the client service, must present a valid digital certificate, and Bob, the server, must also present his certificate. They rigorously check each other's IDs. It operates exactly like a strict secret handshake at the door of a club. If a rogue device tries to connect to your backend API without a valid client certificate, the connection is instantly rejected before a single byte of application data is transmitted.
If we compare the two side by side, we can see exactly where MTLS shines. Both protocols encrypt your data, and both require the server to prove its identity. But the defining feature, the whole point of MTLS, is that the client must also cryptographically prove its identity using a certificate. Standard TLS is built for your public-facing web browsing. MTLS, on the other hand, is the absolute gold standard for service-to-service APIs, especially if you're building financial, healthcare, or complex microservice architectures. Now, the trade-off here, and there's always a trade-off, right, is complexity. Setting up MTLS requires you to basically act as your own certificate authority to issue, rotate, and manage all those client certificates. It definitely adds operational overhead, but in exchange it gives you incredibly fine-grained cryptographic control over every single connection happening in your network.
And that brings us to our final section, Part 5, TLS in practice.
So how do we actually build this in a real-world deployment? It's one thing to sit here and understand the math and the handshakes, but as developers and architects, we have to actually put TLS into practice. When users connect to your application securely, that encrypted connection has to end somewhere so your application logic can actually read the plain text data and do its job. This is called terminating TLS. You generally have two main options here. Option 1, you can terminate TLS right at the front door of your infrastructure using an ingress controller like Nginx or Traefik, which is extremely common in Kubernetes environments. This is generally fantastic because it centralizes everything and hugely simplifies your certificate management. Option 2, you terminate TLS deep inside the app itself, say on port 8043 in a Spring Boot application. Now, while this ensures traffic is encrypted all the way down to the specific pod, it is significantly harder to scale. You have to manually manage individual key stores and certificate renewals for every single microservice, which can quickly become an absolute operational nightmare. For most modern architectures, terminating at the ingress or utilizing a service mesh to handle MTLS transparently is the much preferred route.
So we have clearly established today that the public internet is a hostile, incredibly noisy city. We know to use standard TLS to protect our data in transit from eavesdropping, from tampering, and from impersonation, but I want to leave you with this final, provocative thought to chew on. You trust the outside internet to be hostile, but is your internal network actually as safe as you think it is? Are your internal microservices just blindly trusting any connection that happens to reach them? Or are you actively enforcing strict identity and encryption with tools like MTLS? True security isn't just about building a massive, strong outer wall. It's about ensuring every single conversation, even the ones happening deep inside the house, is strictly verified and protected. Keep that in mind as you sit down to design your next big system. Thanks for joining this explainer.